Today, we're going to do some homework problems. This is the earliest one that we saw, Chapter 5, Section 3, Problem 2. We've got a graph of acres defaced per million tons. This is the rate at which we deface acres with respect to the million tons of coal that we're mining. So let's first translate the graph into a table of values, because that's how this is going to operate. We don't have any kind of mechanism for coming up with a formula for this function. Let's just grab some values and make an approximation. So it looks like if we extract 0 million tons of coal extracted, measured from present day, then it looks like the graph is telling us that I'll be 0.2 acres defaced. And then I'm just going to try to get values for the 1, 2, 3, 4, and 5. So we have to come up with a value for what's going on at 1. And we have to estimate what that is. So I'm going to estimate that to be, I think I used 0.5 when I did the problem. And then on 2, when x is equal to 2 million tons, then we are defacing 1 acre per million tons. And then at 3, it looks like we're going through 2. And then at 4, now we're in the middle again. It's somewhere between 3 and 4. I think the best that we can hope for between 3 and 4 is 3.5. So when x is equal to 4, it looks like we're at 3.5. And then when x is at 5, we are off the map. All right. Let's take a look at what we're going to calculate. Oh, wait, I wanted to make a comment on these numbers. Note that when we were making these numbers, these two were pretty solid. The 1 and the 2, it looks like it really definitely goes right through those intersections. But the 0.5 and the 3.5, those are pretty good estimates. But they're estimates nonetheless. So if it asks us to calculate what I think it asks us to calculate, and our answer is marked incorrect, then that's a place that we could, here at the 0.5 and the 3.5 is a place that we could start making adjustments if we're close. Maybe our 0.5, maybe they read it as a 0.4, or maybe the 3.5 was a 3.6. I think it would be unreasonable to do anything but 0.5 and 3.5. It's about halfway in between. If they're reading it as 3.4, I think they're being too picky. They know too much about their own problem for their own good to be writing problems about it. But these are the most questionable. And this one too. But these two, the 1.0 and 2.0, I think those are spot on. So let's talk about the rest of the structure of this problem. Notice that acres defaced per million tons, this is the rate of change of acres defaced with respect to the million tons of coal we extract. So I read this, especially because it's got this per right in the middle. The graph is a rate of change. So this is the rate of change. Of acres defaced. So the graph that we're looking at is a graph of a derivative. And in calculus class, there are two things that we're going to be asking about when we have the graph of a derivative. We're either going to be asking for the slope of the line at a point or the area under a curve and above an interval. So since this is chapter 5, the definite integral, probably the second one. And specifically, if we think about the area under the curve between 0 and 4 million tons of coal, the area will be the function multiplied by the delta x. Since the function is being measured in acres defaced per million tons, so it'll just be acres per, there'll be some number. that we're going to have to calculate, but it's the units are acres defaced per million tons. That's the length. And then we multiply by the width, which is million tons. Then what happens is the million tons cancel out, and the area will just give us the number of acres defaced. So it's important to understand what we can do with the problem before we start looking at the questions and just trying to answer those questions. If we think about the meta problem, we are in a calculus class and we're looking at the graph of a derivative, or we're just looking at a graph. I either want the area under that curve or I want the slope of the line tangent to that curve. And those are the two big candidates that we have for what we want to do. That's the meta problem. This specific problem, the graph is that of a rate of change, and we do in fact want the area under the curve, because we know that the area under the rate of change will give us the amount of change in the function. So let's look at what the first problem says. This is all before I even read what the problem was. So estimate the total number of acres defaced in extracting the next 4 million tons of coal. Draw 4 rectangles under the curve and compute the area. So draw 4 rectangles under the curve. So what we're going to do is we're going to use the data that we collected, and we're just going to estimate the area under the curve. So part A, find the area under the curve. So you could do 4 rectangles. Our delta, we have 4 rectangles, 1, 2, 3, 4. It looks like our delta x is going to be 1, so 4 rectangles. And our delta x is going to be 1 million tons. So I could use the left endpoints for my, and since the function is increasing, that will be an underestimate. Our delta x is 1, and our left endpoints are 0.2, 0.5, 1, and 2. So we got 2, 3.7.
7.2.
So there are our left endpoints are going to be telling us 3.7, and the units will be acres. If we look for an overestimate, since the function is increasing, that will be the right endpoints. So if we go for an over, that'll be from the right side. Our delta x is still 1, and I'll factor that out. But now I'll use the right endpoints. So 0.5, 1, 2, and 3.5. So this one's going to give me what? 4, 5, 6, 7. Any questions? So here's why we may have got this problem incorrect. Apparently, they disagree that this 0.5 was a 0.5, and they think it was a 0.4. So little secret, Wiley read that as 0.4. So when I go to check my answer, it's going to mark 3. Oh, I'm sorry. The A was the under, and I skipped. I forgot to mention that the overestimate was the B. So part B was the overestimate. A was the asked for 4 rectangles under. B asked for 4 rectangles over. So sorry about that. So we check our answers here, and these are incorrect. Let me explain why these are incorrect. These are incorrect because Wiley said, no, that's not 0.5, that's 0.4. And this problem is being run by a computer, and the computer is like, is it not obvious that that is 0.4? And you're like, oh no, I'm looking at it with the human eyes. And then the computer just rolls its digital eyes at you. Says, oh, dumbass humans cannot tell 0.5 from 0.4. And I'm like, oh, dude, you wrote the problem. But anyway, so the actual answer is 3.6. And that will show up over here. And if we just drop that by 0.4, we get the actual answer of 6.9. So the reason, if you're getting these problems wrong, the reason that you're getting these problems wrong is that the point is not 1 and 0.5. Is that this point here, it should be 1 and 0.4.
Is the 3.5 correct?
The 3.5, it looks like the 3.5 is incorrect because if I drop a 0.5 down to a 0.4, then the 3.5 still holds up with a 6.9. So it looks like the 3.5 is still okay. Any questions? Comments? Snide remarks?
Yeah, 0.1 is a repeating decimal in binary.
So one of the this is one of the things that's why I had to switch to unlimited attempts, because the default tolerance, which I could not find how to change, by the way, that's on me. That's my fault. But the default tolerance is plus or minus 2%. And whoever wrote this problem, they're like, oh, 2% sounds good. 2% means that you have to get this exactly right. You have to drop a 0.4 in here, because 2% of 3.6 is 0.072. So if you put this up by 1, you're too far. You're going to be too far away. So someone wrote this problem, but they didn't think about what the problem represents. They didn't think about what could happen on the problem. They just kind of put this outside measure of like, oh, 2% is good, but it's not. It means that if the 2% tolerance on this problem means there is no tolerance on this problem. So, and zero tolerance is always unhealthy. Any questions? Okay, so that's my note on this problem, and I'm glad that this one came up because this one's really hard to land because of this has to happen. Okay, so our answer was off because we read the 0.4. What Wiley thought was a 0.4, we read as 0.5. So if the problem was being scored by humans, like if it was me, I would look at this and like, oh yeah, 0.5, that's totally reasonable. And if someone put 0.4, I would actually think, 0.4, okay, I'll buy that. It's a little bit under the bottom, under the halfway. But if you're like, oh, 0.7, then it'd be like, oh no, that's ridiculous. It's not past halfway. You need to go back and review your decimals. Any questions on problem 2? All right, and then you just have to find the average of those two. All right.
Yeah, I just inserted the numbers. It said 3.6 was incorrect and 3.7 was correct.
It did? I have,
Yeah.
mine says 3.6, so
Well,
I'm
it's
just
not
going with,
inconsistent.
good job, Wiley. Maybe it's trying to be like a variable to simulate human error, which is even more creepy because we know AI is getting a lot better at doing things. All right, let's do some more problems. Incidentally, I love that the snide remark was not actually snide in its content. It was just snide in its delivery, which was, I think, perfect. I was like spot on. I don't know if that's what you were going for, but that's what I got. So yes.
If I'm going to be mocking computers, it's going to be for the inefficiencies of their counting system.
Computers and the way they count. It's so cute, isn't it? So let's talk about chapter 5, section 3. Oh, man. Oh, that looks terrible. Oh, well. Of course it looks terrible. I wrote it. If you jump out of an airplane and your parachute fails to open, I love how this problem just leads with disaster. If you jump out of an airplane and your parachute fails to open, because this is the first thought I would have if I jumped out of an airplane and my parachute failed to open, I go, what an interesting problem I have been faced with. I'll have to be sure to record this one and pose it as a problem to my students. Your downward velocity, t seconds after the jump, is approximated for g equals 9.8 meters per second and k equals 0.2. K should not be in seconds. Oh, well. So we have a function, v of t. At least we get the message. So g is 9.8, so I'm going to divide that by the 0.2. That'll be 4.9, so 49, is that right? Times 1 minus e to the negative 0.2t. All right. So this is going to be your velocity in at t seconds. So it's your velocity. Gravity is being measured in meters per second squared, and time is being measured in seconds. So this must be your velocity. The first thing that we have to conclude is that this is going to be velocity. All right, we didn't have to conclude that it's velocity. We were told that. But the first thing that we have to conclude is that this is in meters per second. So whatever this graph looks like, we need to write an expression for the distance that we fall in t seconds. So velocity is the rate of change of our distance. So this is the rate of change of our distance. So we know that if we integrate the rate of change of the distance over an interval, we'll get the change in distance over that interval. So I want to integrate, we want to integrate our velocity with respect to time, starting from the time we jump out of a plane. We'll have to assume that that starts off at 0 seconds. And then we fall for capital T seconds. So the definite integral of our rate of change will be our change in distance from 0 seconds to capital T seconds. If we integrate the rate of change of the distance, that's this function right here. If we integrate the rate of change of the distance, that'll give us the change in the distance over that interval.
Hey, Professor, is that the right equation? Because I'm showing v of t equals g over k times 1 e.
Yeah, G is 9.8 meters per second and K is 0.2 per second.
Mhm.
So G over K is 9.8 over 0.2.
Okay.
So G is, G is 9.8 and K is 0.2. So G over K, oops, I spelled K wrong, is 9.8 divided by the 0.2. And that's where I got the 49.
Oh, gotcha. Thank you.
All right. In question 5, any questions on 4 before I just cruise on to the next one? I think this is one of the choices. I think this was multiple choice. Can't always remember.
It is.
Cool. All right. So let little f be f prime. So we're going to let little f of t is f prime of t. And capital F of t is 4t squared minus 6t to the 5th plus 6t. And then evaluate the following integral using the fundamental theorem of calculus. So we want to integrate from -2 to 1 little f of t dt. So the fundamental theorem of calculus says that if we integrate little f, we can evaluate its antiderivative at the end points. So little f of t is capital F prime. So this is the integral from -2 to 1 of capital F prime of t. So we can evaluate this definite integral by looking at the antiderivative of this derivative at the endpoints. So the idea is that we don't need to take the derivative of this because we're just going to end up finding an antiderivative and end up back where we started. So we're just going to calculate capital F at 1 and subtract capital F at -2. Okay, so we could set up the problem by saying, well, I need to find out what little f of t is. I should make my little f's more little f. There we go. We could say, oh, I got to find out what little f of t is, and little f of t is the derivative of capital F, and then take the derivative of capital F. But then I look at this context and say, I'm just going to be integrating little f, and that's just going to be back to capital F. So I just need to evaluate this function at 1, then this function at -2, and then subtract the results. So we would just need to do 4 times 1 squared minus 6 times 1 to the 5th plus 6 times 1 minus 4 times a -2 squared minus 6 times -2 to the 5th plus 6 times -2. We evaluate f of 1, or capital F at 1, capital F at 2, and then just subtract the results. And this looks like a job for calculator. Oops, scroll. There we go. Any questions? In problem 6 from this section, we have a table of values. And so all we have to do is left and right this table of values. This one goes up and down, so maybe we won't be able to get away with just left and right. Let's find out. Either way, I see a table of values. I know I'm going to be making rectangles. Our function is our year in one category, so 1970, 1975. I'm not going to write all of them. And our emissions, E, is 26.9, 26.2, and 27.4. All right, and then it goes on. I think this will have enough information to make my point. What we need to note is what these functions represent. So the emissions is nitrogen oxides in millions of metric tons per year. So the units here on E are millions of metric tons per year. Million metric tons per year. So E is a rate of change of metric tons with respect to the years. So E is a rate of change of million metric tons. That's what we want to notice. E is a rate of change So in the table, we are looking at the derivative. It's the rate of change of million of metric tons with respect to the year. All right. So to find, and the x is measured, or the input is measured in years. So when we calculate the area under the curve, or the definite integral will be in million metric tons per year times years, and then the years will cancel out. So the definite integral will be in million metric tons. So if we take units that are million metric tons per year, and multiply by the years, then the years will cancel out and we're just left with million metric tons. So integrating will tell us million metric tons. So the next one says to estimate the integral using the average of the left and right hand sums and round to one decimal place. So here we're just going to do a left and right thing. I was concerned because the function doesn't go just, is not monotone, doesn't always increase or always decrease. So it goes from 26.9, it drops down to 26.2, then jumps up to 27.4. So if we were going to do, if we had specifically requested a lower and an upper bound, from 1970 to 1975, the lower bound is on the right and the upper bound is on the left. But from 1975 to 1980, the lower bound is on the left and the upper bound is on the right. That's not important for this particular problem because we're just directed to do left and right. So just do 26.9 plus 26.2 plus 27.4 plus all the ones except the last one. Add those up and multiply by 5. Because that's all we're doing when we're integrating anyway, is just adding up a bunch of values of the function. Any questions? Great. How's everybody okay? 7 minutes. I think we can get through it. Right. Let's see. I think from section 4, we've got 4 and 5 and 6. Four and 5 and 6. Four was from yesterday. I should probably start there. All right. So we're told that f of x is even. So that's a big deal. We've given a big piece of information here. F of x is even. So we got to think about what it means when we have a function that is even. Then we got to think about what that will mean in terms of the graph of the function. So let's load up our definitions of f of x is even. So the definition of f of x being even is that f of negative x, even in odd functions, the question is, what happens when you plug in the opposite? In an even function, f of negative x just gives you f of x. Even functions don't care about changing the sign of the input. Even function would be something like f of x equals x squared. F of 2 is 4. F of negative 2 is 4. Even functions don't respect negatives. Change the sign, they're like, oh, no, make it positive. Even functions are your friend that are always just like, oh, cheer up. And you're like, oh, no, I'm angry right now, or no, I'm sad right now. And eventually I will not be sad. So stop forcing me to cheer up. Don't get to try to dictate my mood. You know what I'm talking about? So f of x is even. So that means f of negative x is f of x. Don't be mean, they're just trying to help. F of negative x is f of x. What that means in terms of the graph is that we have symmetry about the y-axis. We have vertical symmetry. So that means the graph has vertical symmetry. That is about the y-axis. So visually, if we look at a function that is even, whatever shows up on the left side of the graph, that's the right side. Whatever shows up on the right side of the graph, the left side is a mirror image of the right side. I should start with the left side. It's hard to mirror this direction. So the left side is a mirror image of the right side. The left is a mirror image of the right side. This is also called MCU symmetry, because when you make a movie in the MCU, the villain is just a copy and paste of the hero multiplied by -1, so they'll be in opposition. And in the good version of that, the villain is correct as well. So,
Not if you use the square root of vibranium.
yeah, but that's way too much math for the MCU. They're like, we need someone to oppose Iron Man. How about another Iron Man? But Iron Man's a good guy. Make a bad guy Iron Man. Okay. Now let's do that for the next 10 years. 12 years? When did Iron Man come out? 2008? Wow. All right. So the left is a mirror image of the right. So what does this mean in terms of integrals? That's what we care about now. What's this mean for integrals? So this means that, oh darn, we're out of time. So here's the question that we were going to be left with. What does this mean for integrals? We've got the picture of this now. Take a look at how the integral is set up in this problem. Okay. In particular, the integral from, say, -4 down here to 4, the mirror up here, of an even function, dx. Any questions?
I have a question.
Yes,
When is the homework due?
it's listed on there.
So it's all due on February 1st?
Yes,
Okay. Okay.
if
just
that's
making
what's
sure.
listed there. I can't quite remember.
Yeah, it's listed there. I was just curious. I thought you said that they were due later than that or something. I wasn't sure.
No, I said that the homework policy that was in place for Chapter 5 and Chapter 6 means that you're going to be cut off from making submissions on Chapter 5 and Chapter 6 after the due date.
Okay.
But moving forward, you're going to be able to submit homework after the due date, but for a reduced score. But I always have very long due dates. So if you're in the place where you're taking penalties on your homework score, you're a couple of weeks late. So,
Just making sure. Thanks.
yep. So think about what this symmetry is going to mean for areas when we go from a number, an opposite, between opposites, from -4 to 4. Any questions?
I have a question on the quiz, if that's not out of bounds.
What's your question?
I submitted it last night, and I also did quiz 2, but I'm not sure if you're going to have an opportunity to grade those before the deadline tonight.
I graded anything that was submitted last night this morning.
Oh, I'll check. Thank you.
I was surprised too, so I don't usually do that. So keep in mind, Robert Downey Jr. was Iron Man for 11 years so far. I calculate the probability of Robert Downey Jr. not being Iron Man anymore as being close to 0. So they're going to bring him back. I mean, that's what they always do. He's like the Jack Sparrow of this universe. It's like, oh, they like that? More of that then. You know what I mean?
Thanks to
All right.
Amber Heard, that's not going to happen.
I dollars to donuts, it's gonna happen. If they make more movies in the MCU, he's coming back. They have to.
I think we're going to have more Robert Downey Jr. playing Iron Man. Yes. So as a full-fledged character, I think they're trying not to do that cheat, but it is comics.
Yeah, he might not be a full character. They're not going to make an Iron Man 4, but he is going to show up. At the very least, he's going to show up as a cameo. If they take stuff that he recorded before and just replay it, that counts. Because they can't turn away from the golden goose. Anyway, that's going to do it for today. I will catch you cats on the flip side, and thanks for playing.